Okay, so Ayecka is a communication solution company. We started with doing some communication modems, and the company during the years evolved to supply complete terminals, complete links, complete systems. And in recent years, we are focusing on the new space business. And today I will talk about communication solutions for LEO satellites, and specifically for small satellites, nano satellites, micro satellites, and so on, like Meir mentioned before. But before I start, I added 2 slides to explain what is a revolution in this market, because we are witnessing a real revolution. So here you can see a constellation of small satellites, and these small satellites are not only small, but they are also orbiting at a very a low height, typically between 500 to 1,000 kilometers. And what is happening when you take down the satellites to these heights, that instead of being just an RF relay like a geosynchronous satellite, they become a part of the communication infrastructure. So the pioneers in this field, like Meir and other people here that started with small satellites for some applications, they started by giving a IoT service or maybe imaging service and so on. But when the market started to explode with a huge number of satellites, people start to realize that these satellites can be part of the communication infrastructure. They are in low height, so the latency of passing data through these satellites is very small. So you can use the satellites as part of the communication infrastructure. You can even shorten the latencies compared to delivering data over fiber links. So these satellites become a part of the global infrastructure. And we are just at the beginning of the revolution. In this slide, you can see a few applications like IoT, for sky and space, broadband networks, that we will see later in one of the lectures of a company doing a broadband network, direct to cellular, backhauling. Direct to cellular is even becoming part of the cellular infrastructure. And all of these services or use cases require the satellite to become part of the communication infrastructure. It means that it needs to have communication means and some processing, like a router functionality, and some, or maybe artificial intelligence, what people like to describe today as deep learning or decision making on the satellite itself. Even when we discuss Earth observation satellites, typically these satellites being like a single satellite orbiting the globe, taking picture, downloading the pictures to a gateway station. So this is starting to change. Instead of having a single satellite, we are seeing constellations of Earth observation satellites. And when you go to constellations, like you can see here, a satellite can take an image in one part of the planet, and if you have sufficient number of satellites in your constellation, you can transfer the image in real time through the constellation to the gateway station and download an image in real time, instead of keeping it on the satellite and waiting for the satellite to go over the gateway station. So these Earth observation satellites are going to become also communication devices. They will need very high-speed links to connect the satellites to each other. And even more than that, what we are seeing is a requirement not only to take images and download the images to a processing center, but also to process the images on the satellite in real time and deliver to the end user sufficient information to take decisions. So it means that the Earth observation satellites are becoming a communication device and also a processing or an edge processing device capable of analyzing the images, taking the decisions or recommending decisions, and sending these decisions or recommendation directly to the end user. Imagine an Earth observation satellite taking pictures of the atmosphere, analyzing the pictures, and understanding that there is a storm. It can immediately send the information to a pilot of an aircraft that is going near the storm and help him take a decision to change the height of the flight, change the route, and so on. So this is a completely different use case than what is used today for Earth observation, and all of this require communication and processing. What I will show you today is our OPR, Observe, Process, Report platform that we are building that will enable the owners and operators of these small satellites to do just that, make the satellite a communication device, and also do some analytics on the satellite in order to create real-time decisions. The solutions that we implement in Ayecka, or what we are, our expertise, are communication solutions for small satellites. Small satellite means not only small in size, but also a limited amount of power that can be generated on the satellite. So when you design a communication solution, it needs to be effective in power consumption. You cannot take just any communication solution and use it on the satellite. In many cases, you will not have enough power from the solar panels to process the signals and perform the job. So what we do at Ayecka, we also optimize the power consumption of the communication solution so that we can implement them on the small nano and micro satellites. We have made several solutions. The first one is the high-speed communication links that are designed for communication networks and Earth observation, high-efficiency communication networks that are designed for IoT, and the OPR, Observe, Process, Report, edge computing system, and real-time messaging for the application I described before. And we also have a range of user terminals. So we try to provide a complete ecosystem for the satellite operator. Our first and most popular solution, the fiber speed link, is a communication link between a LEO satellite and a gateway station. And this link provides up to 2 gigabit per second downlink data from the LEO satellite to the ground, and up to 100 megabit per second from the ground to the satellite. And this is specifically designed for Earth observation, where you need to collect a lot of data when the satellite orbits the planet, and then download this data fast when the satellite go above the gateway station. And this solution is composed of a modemware, which is the firmware and software that is installed on the satellite payload, and the gateway station that you can see also at the exhibition outside. Together it forms a complete communication link. And this solution is implemented on a medium scale FPGA, power consumption of maybe 7 or 8 watt, something like that. Recently, we succeeded to develop a new solution. We call it the fiber duplex link, and this enables us not only to download 2 gigabit per second from the satellite to the ground, but also to uplink up to 2 gigabit per second from the gateway station to the satellite. And this is essential if you want to build a broadband communication system with a LEO constellation. You need not only to download high speeds, but also to upload, because it's a symmetrical network. Again, the problem here is to make it efficient and with low power consumption on the satellite. And what we have done with our new proprietary waveform is a solution that you can implement on a medium scale FPGA, specifically in RF SOC, with a consumption of also 8-10 watt. That's all. You can have a duplex link fiber speed to the satellite. Once this is available, now we can think about satellite constellations. For example, for broadband networks, where you need to connect satellites to each other in space in order to pass user data, like with the Starlink network. To do that, high-speed links are required between the satellites. And this new technology enables us to provide 2 or 4 gigabit per second ISL links between the satellites. And when you think about Earth observation, next generation, real-time Earth observation, you take a picture here, you pass it through the satellites to another place. You also need high-speed data links. So this is the key enabler for this type of satellites with relatively low power consumption. Now we move to the other part of the spectrum, from broadband to narrowband. Also for this we have a solution that we designed together with Sky and Space. And this solution, what we call the IoT efficient network, is designed for IoT constellations. IoT constellations, on the contrary of Earth observation or broadband network, they need to collect small amount of data from huge number of user terminals. And this small amount of data are transmitted when the satellite hovers above the user terminals, and when the terminals have something to send. So you don't really know when. The situation is that the satellite passes over the planet, and many users are transmitting small amount of data. And we need to collect this data efficiently because the frequency capacity is always limited. It requires licensing, so it's always a bottleneck. And for that, we are implementing a technology that is called CDMA multi-channel. It can be implemented on a very small FPGA. FPGA is a kind of an ASIC device, very few watts in space. And this gives a fairly good solution to collect information from the user devices. Applications for this type of solution: fishing, low-cost fishing, fisher boats, and even in the future, connected cars. Imagine a world with 50% of the cars are autonomous cars. To this or that level, all of these cars will need connectivity. And this connectivity is not necessarily broadband. It can be IoT, like we learned in the first lecture. And this system is designed for this type of data. Again, can be implemented on a very small 3U or 6U satellite with low power consumption. Our next generation system, also for IoT type of networks, is called the MAPS, multi-app satellite payload. We are now designing a new payload that will go on the satellite. And this payload includes a very strong processor. This processor is a new FPGA from AMD, which includes a very large number of generic FPGA processing, but also what they call AI engines, which is a type of a GPU, and strong ARM processor. So imagine a processing block which has a power of a computer server that you would usually put in the server farm. So imagine this kind of server with very efficient power consumption integrated on a small satellite. Add to that communication devices, add to that cameras or sensors, and imagine what kind of applications can be implemented on the next generation satellites with a mapped type of payload. So for example, you could do an efficient communication network like we are doing with the CDMA multi-user solution, which will support millions of terminals. But you could also do image processing, decision making, analytics, and send decisions directly to the end user. Things that are not done today. And when we start to imagine what would be possible to be implemented on this type of networks, we can only imagine a small part. What we believe that once this type of solution is available on small satellite constellations, the amount of new applications will be enormous. And eventually, companies like Sky and Space and others will sell a service of processing power in space with sensors and communication. And there will be many, many companies that are building applications. Very much the same to what is happening today on the cellular networks, on the user devices. It will be just the same, only that the applications will run on the satellite and will give new type of services that are not possible today. So here you can see an illustration of an Earth observation device, like a camera or a multispectral imager, the MAPS platform, a small satellite, user device that can be that you can communicate to from the satellite in real time, and the gateway station where you can download the raw data for further processing. And this is a very important building block in the next generation of small satellites. From the user devices, we also have here outside, so you also the mega modem that works up to 2 gigabit per second for the gateway station. On the other end, the small S-band device that can be installed on fishing boats, on cars, for agriculture, and many other applications. We are now also building a new Ka-band tracking device for broadband networks. And we have also solutions for airborne, like this one, and that one with a phased array antenna, and a very popular modem that goes to gateway as a service type of companies, not only for our satellites, but for many other satellites. Few examples that, of customers we are working with. So Sky and Space by Meir, a company building an IoT network where we provide the user terminals and the modem that goes on the satellite itself for IoT. Earth observation customer that uses the fiber speed link to download the data from the satellite to the gateway station. thank you very much for listening. If you have any questions. We have a recess now of a few minutes, 20 minutes. שאלות? Yes. Leo to Geo. I don't know. We have one, but that's a good question. We have one customer. Don't know if you know, but a few years ago we supplied to the International Space Station a LEO to GEO communication link. It works for the cosmonauts, not for the astronauts. And this goes up to 100 megabit per second. That's a Leo to Geo link. So we had one customer. Yeah, we had one customer with a big Leo. That's the ISS. I know that there was a company trying to do a MEO network, which was called Link Stars or something like that. They closed the company recently, but they meant to do LEO to MEO and MEO to ground or MEO to GEO in order to provide the infrastructure to connect LEO satellites through MEO satellites. But right now, I'm not aware of any such project that is still alive. We made a 100 megabit per second link. So it's doable. It depends on the available bandwidth on the GEO satellite that you have. Yes?
Ask about the maps. Like, you have a very strong computer that uses very little energy, but what's the trade-off? Why don't we have such a wonder here on Earth?
Okay, so the Maps is a new platform that we are building, and it is basically a very strong FPGA device together with some RF components that enable it to connect to an antenna. So that on this Maps platform you can run a communication modem and router for communicating with the ground terminals or with the ground station. But you can also run some analytics. So the particular device that we are using is called a Versal Premium AI FPGA. And it includes, it's a big machine in a small package that is also suitable for space applications. So it's what we call radiation tolerant, which means that it's not so sensitive to space radiation and can be used in space. Okay, more questions? Okay, so thank you very much.